Hi, my name is Anatoly, and today we're going to talk about machine learning. This is ABC to DEF. I'm sure you guys got that. Before we start, I'd like to thank Cherry Solutions as the company I work for and the company which has hosted this conference, and the conference is, of course, PhilET. So I'd like to thank them both. And let me start by telling you a story of Groot, but not just some Groot. It's a guardian of the galaxy, but not just some galaxy. It's the guardian of my galaxy, right? So meet Groot. This is Groot. Groot is this little Raspberry Pi camera that I built to guard, a very important corner of the galaxy, and it lives right here on my door. And the task that Groot has is to, see if there are any strangers and inform me if it sees something interesting. And it has a motion software installed, which is able to detect motion and take pictures and save pictures when it detects the motion. And of course, what I wanted to detect, right, is this, right? If somebody is right next or right behind my door, with good or bad intention, any intention is good enough for me to detect. But unfortunately, what it does detect is this, right? It detects cars, grass, trees. It does detect humans as well, but not as eloquently and precisely as I would like it to. So why would I even want to detect a human? So maybe I'd like to classify it later as family, friend, package delivery. Of course, I want to be safe. If somebody rings the doorbell at 3 o'clock in the morning, I'd love to know who that is. Since it detects all the cars and trees and grass and all that, it creates a lot of noise because it saves all those pictures, sends it to the backup servers and all that. So I'd like to get rid of that. So what do we do when we need to do something, right? We go to Google. And I went to Google, it was some years ago, and I said, I was thinking if I need to detect humans, I would probably need to focus on faces. Because I heard about that thing called facial recognition, and I think humans have faces, and trees and cars, they just don't have faces. So I thought that I'll ask Google to see if Google can help me to detect faces. So Google said, try these. There's Google Vision API from Google Cloud, OpenCV, TensorFlow, and all that. So I did try them. I went through, all the beginner tutorials, and I tried them as hard as I could. And after trying all of them, I figured that the best model here to use is this. It's called the Door Viewer. It's actually pretty cool. It has a very great properties. It's very, very low latency, very high accuracy. You can install it right in your door, right? So you can just look into it and detect humans like you'd never believe. Because you're very good at detecting humans. So I highly recommend this. If you ever have this problem, this is probably a very good solution, very stable. So why did these tools fail me? Why? I mean, these are all great tools, right? And Google is rarely wrong. So let's see. Well, first of all, I had no clue how to use them. Of course, 2, 3 weeks, even a month, even a 2 month. In this is not a simple subject, right? So it doesn't really empower me well enough to use them properly. So I didn't use those tools properly. And the second is camera images tend to be very low quality, and especially if the human is in a distance far, far away. The face is no more than 5, 6 pixels. It's very hard to make out the face. But the main problem with this approach is that myself, I decided that in order to detect humans, I need to detect faces, right? So this is something that's called feature engineering. I'm going to introduce some jargon, but this is the first kind of jargon. So face is a feature of a human. I decided that this feature is most important and more important than other features. And I kind of engineered this into my problem. So that's called the feature engineering. So we'll come back to Groot, and we'll see how it's solved. But before, as Dan mentioned, we'll try to understand what the neural network is. And here I mean the artificial neural network, right? And usually, I mean, when I started on this path, it was some years ago. There was not exactly, those fun and cool JavaScripty things available where you can go and see, oh, that's what neural network is. It was mostly white papers, right? And going through white papers, it's depending on your depth and math and all that, it may be fun, maybe not. But after going through some of them, and again and again and again, I had this feeling that neural networks could be, not exactly easy to grasp. This is the initial intuition I got, right? So here, one of the things I'd like to do right now is to to create this intuitive feeling of what neural network is first, right? We're not going to talk about math a lot or anything like that. I just want to see if we can, get into the neural network and live there a little bit and understand what it is. So we're going to write this problem. We're going to solve this problem, and we're going to do this. We're going to write a product that's called TensorFlow. And this is a simple kind of experiment. So you have a student and you have a teacher, right? And the student needs to pass a test. And the test has, let's say, 42 questions. And if you're a computer programmer, 42 is the only number you should use, right? So 42 questions. And the desired grade, of course, 100. If you want to take a test and you want to pass a test, the 100 is the maximum grade you strive for. The only caveat here, the teacher is so great that she allows you to take it 5 times. So you took it one time, you got 72%. And then you can learn and kind of look back on your mistakes and try it again. So this is what we're going to do right now. We're going to see if we can build something that's going to take these 42 questions, give it to a teacher, and we'll try it 5 times. So this is a student. She's working on her test. Let's give her some time because it's not an easy task. I think she's produced something. Let's see. Okay, so she took all these 42 answers, 42 questions, and produced answers to all of them, right? The best she could, right? So she predicted that these are the answers. And then she turns it into the teacher, right? So this is exactly the same thing, it's just a little more visual. Then the teacher takes the test and looks at all the answers, and the teacher knows the correct answers, right? And the teacher marks what answers are correct, what answers are incorrect. And then using some kind of formula that we all know because we went to school, and this is usually how it works. It takes correct answers divided by incorrect answers, total answers, and this is the final grade. And remember, we strive for 100, right? So teacher returns the test back to the student, and student hits the books, looks at what student did incorrectly, and tries it again. And now I'm going to introduce some more jargon. So this is the basic premise, right? So this going back and propagating those questions back from a teacher to a student, and student hitting the books and try to understand what she can do better is called back propagation, right? And the answers that student gave are called predictions, right? In statistics, predictions are marked as y hat. Y hat, I don't know, but that's what they're marked as. So the other thing that's one of the most important things is a loss function. So here we're taking the same example as we looked at before, the 76%, but we inverted it a little bit. We're saying not how much the student won, but how much the student lost, right? So she lost at this particular take, she lost 23.8%, right? And that's called the loss function. So so far we're using the same function that we all do when we write tests. We're taking 100% and we subtract that 6.2% that we got. And that number 23.8 is called the loss, right? So far we have backpropagation, y hat is a prediction, and the loss function with a loss. And the number of times we're taking this test is called epoch, right? So you can take it. So here we have 5 epochs. So let's dive into something a little more interesting. So the whole thing is called the training, and the point of the training is to drive that loss down, right? It's kind of obvious, right? Because if you lost 23.whatever%, next time you take the test, maybe you want to lose less, right? You always want to lose less, and that's the whole point of the training. So as you train more and more, you do better and you lose less. So while the function that the teacher kind of uses is okay, it has a slight problem, right? Let's say the student answered the question almost correctly. So let's say we have, so here you can see that the student answered 23.9, but the answer was, 23.5, but the answer was 23.9. So the student was kind of close to an answer, right? In the teacher formula, the way the teacher marks the test, she would mark it completely incorrect, right? So we want to come up with a better loss function. We want to come up with a better formula to see how close a student was to an answer, right? It's gonna tell us a better kind of outcome, because if some other student answered 0 here, then it's more incorrect than 23.5. And this is the function that's called mean squared error, and it's a very common function that's used in neural networks and machine learning. And even though it looks a little scary if you're not a mathy person, there's nothing scary about it. So these are the predictions, right? These are the actuals. and then you subtract and you square them. So basically you're finding the difference, right? The reason you square them is twofold. First of all, you'd like them to be positive, right? That's why you square them. But second of all, the square actually highlights how far you are from the truth. So if let's say, if I didn't square, I would be, 2 far from the truth. But if I square it, it's 4, and it's 16, or it's 64, and so forth. So it just shows you a better distance. So we use the formula here, calculate it, take a mean, and this is our loss. It means nothing, just a number. The whole point is to drive it down. And this particular function, again, this is a very common function to use that's used in machine learning. And this common function, this function is used for problems that are called regression problems. And regression problems are when you need to predict something continuous, right? So, for example, salary or approval rating or distance, and you kind of have this intuitive feeling why, right? Because this function shows you how far are you from the answer, right? So this is a very common function. So another function, and I promise you this is the last piece of somewhat understandable math, is called log loss or cross entropy, right? So this function is used to predict whether something belongs to a particular category, which is classification. So let's say one of these questions that the student had was not just whether it's solve this equation or something like that. It was just pictures. So one of them was cat, another one was dog, and the student should have answered. And we say that if you think it's a cat, put 0 there. If you think it's a dog, put 1 there, right? So these are called labels, and the student sees that it's a cat in this case, and for some reason she thinks that it's a dog, and she's sure, like almost 80% sure that it's a dog. In the second picture it's a dog, and she's also almost sure that it's a dog, right? So we should have a function that kind of punishes the first one answer and kind of not punishes the second answer. If you look at this function more closely, you can see that it's just mathematical way of saying this, right? Of mathematical way of having an if statement. So if you look here, if y is 0, right, the whole thing becomes 0. So we're using this part of the formula. If y is 1, well, the whole part goes to 0, and we're using the left part of the formula. Basically, if we know that you're predicting for a cat, say how catty the answer is. If we know that we're predicting for a dog, say how doggy or non-catty. That's what 1 minus y, right here, 1 minus y is. The answer is. So this is, while it's look mathy and there's logarithms and all that and minus in between, it really just this. If it's a dog, see how well was predicted that it's a dog and so forth, and it's a cat, do the reverse. So the calculations themselves don't really matter, but this is the number, right? This is not exactly the percentage or how far. This is just the number that we need to drive down. And as I mentioned, this particular function is also very, very common. It's called, usually it's referred to log loss or negative log loss or just cross entropy, right? And cross entropy is usually used for problems of classification. Problem of classification is when you need to predict that something belongs to a particular type, right? It's no longer how far something is from somewhere or the price. Is it just you have several types of something or 2 types of something is here? That's why it's binary. And this function allows you to predict whether, this loss function allows you to predict whether something belongs to a particular category more than it belongs to other categories, right? All right, and you can see that there's a slight hint here. There's a human versus non-human. Maybe it'll help us to figure out, to detect our humans better. Okay, so this is our neural network, and there's a slight problem here. I mean, everything is fine. The student can write test fine. She has, somewhat good grade. She has like 78.2, let's say, and she cannot go farther than that. No matter how many times she takes the test, she just cannot go, because certain questions are not very, she's not very well versed in geography, for example, right? So, or something else, right? So what to do? What would you guys do besides Googling? Exactly right. You would talk to a friend, right? So you would say, I have a friend and she knows about geography. So let me write all the answers that I know and some answers that I don't know, but I'll try to do my best. And I'll pass it over to a friend. And the friend will take my answers and questions and try to do better, right? Try to add the domain knowledge that friend has. And you probably already know what's going to happen next, because that friend has another friend. And that another friend has more friends and so forth. So there's a lot of friends. It's a team effort, right? Friends working together. And then only the final result is then turned into the teacher, right? So there's a lot of friends, a lot of brain power, and they all kind of specialize in their own things, and they hand in the test. So you can see that probably the chances are higher that we can do better, right? And remember, there's this thing called back propagation, where the teacher grades the test and gives it back to the student. In this case, it's almost the same thing, but it just gives it back to every party involved, right? Every friend. So every friend can kind of look back and see what the friend can do better. So all the stages, right, are called layers, and all the stages in between, if we add friends between student and teacher, are called hidden layers. And if there are hidden layers, they're hidden inside, they're deep inside, okay, we call it a deep neural network, right, because we have hidden layers. If it was just student and teacher, it would still be a neural network, it would be called neural network, and later you'll see why, but it would not be a deep neural network, and this would not be a deep learning. So if you say you're a deep learning expert, that means you know that there are some hidden layers. Doesn't mean that you're expert in anything really before you prove yourself, but it just means that you know that there are some hidden layers in the neural network. That's what deep means here. So good. So we have this intuitive take on neural network, at least in the initial intuitive take on neural network. We got some jargon. You don't have to remember it or think, oh, I forgot what this is. It doesn't really matter. It just, as long as you understand what's going on, we're on the right path. So time to hit the whiteboard, right? To make it a little more formal. So we now know that there are questions, answers. They fly from left to right from a student to a teacher. So let's like to formalize it a little bit. So if you hit whiteboard and you're talking about networks, of course it's all about circles and lines, right? So just so you guys know, these are circles and these are lines, right? So imagine that these are the answers that student kind of came up with at first, right? She says this question number 15, the answer is 32, right? So this is 32 here, flying out here to this. So this is our first hidden layer, if you will, right? So this is called an input layer, and of course, if there's an input, there's an output layer. But these are called activations, and we'll see why in a second. But basically, don't think too much into that. There's no like graph theory or anything like that. This is just the numbers, or not flying. Well, usually numbers flying into the circles. And what happens next? Next, we have another layer, right? How do we use that other layer? We take each of those circles and we connect to each circles after it, right? And not just connect, because just connecting, I mean, we can pass this x1 down the line, right? But it would not serve any purpose, right? Because we would be passing x1 down the line, and right somewhere here or over there, it would be still x1. Right, so we add something that's called weights to it. Don't think too much about what it is. Think about it as random numbers. So we say this is 0.2, and this is 5.9, and this is -2. It doesn't matter. So these numbers will allow us to not have exactly x1 at the second layer, right? Second layer is right here. And then we connect everything to everything again, right? But moving forward, right, from left to right. And then we connect everything to everything again, and it becomes a neural network, right? So this is output layer. It's the most interesting layer, and this is input layer, and these are those hidden layers. These are those friends helping us out. Okay, but we use some random numbers. We use some inputs. What are these values, right? Well, how do we compute these values? Well, let's focus on a single activation, right? So A stands for activation, and the reason it stands for activation is because whoever came up with this thinks that this is, simulates brain a little bit. But since I don't think anybody really knows how brain works, this is just a legacy of that theory. But this circle is called the neuron, right? And this is called activation. This is when you came up with the idea and your neural spikes or you react to something. So that's why it's called activation. So the weights are flying into this one neuron, right? And the A then is computed like this, right? So some of you who know a little bit about more maybe linear algebra, statistics, math, you probably know this as a dot product, right? Is when you multiply matrices, but it's again irrelevant. It just x times w4 in this case, plus this, and that becomes the A. So if you think about A, kind of encompasses all the knowledge or all those numbers of the layer before. Right, that's how to think about it. And the output is the most interesting. The reason it's most interesting because it's kind of land of loss, right? So this is where you take your output. You say, okay, I expected 42. I wanted you to predict 42, but you gave me 3.14, Not exactly 42. So what can we do? How can we make 3.14 move towards 42? Well, let's look at it. Let's think about it. So we know how A is computed, right? It's like this. So what can we change? We probably won't be able to change A because it's computed, right? It flies through the whole network and it gets computed. But maybe we can change weights because, or parameters, they're also called, because we choose them. Remember I said that they're random numbers, so we choose them. Well, then how do we, so what to do? How do we drive that loss down? Well, it's simple. You just choose better weights, right? Well, it's not simple, right? Because what does it even mean to choose better weights? Do we choose, any numbers? Do we go for, for eternity from minus infinity to infinity? And so what it means is we need to choose better weights to lower the loss, which I already mentioned. But does the loss even depend on weights, right? So the whole point of this exercise is to drive the loss down. The less of the loss, the more accurate we are, right? But does the loss even depend on weights? But let's see. Let's look back at the formula that we already looked at, right? So we have these predictions here, right? And we have the actual values. Well, these predictions, right, this particular value is this activation. It's this 3.14 that we predicted, right? We know how to compute them, right? So if we substitute that prediction in the formula, right, then we see that the loss actually, in fact, depends on weights. So intuitively, somehow we can think if we change those weights a little bit, maybe we can drive that loss down. But how do we change it? How do we approach the problem? Well, imagine that this is a loss function. But most of the functions, the loss function is just a mathematical function. Let's say it's a quadratic function, and let's say that the weights that we gave to this function resulted in this particular value. Let's call it 55. It doesn't matter. So this is the loss, and we're here right now, right, with our initial weights. But we want to be here. We want to be right on the bottom. We want to be where the loss function is the minimal. And sometimes it's called the global minima, and we want to choose the weight so the function has minimal value in this. So how do we get there? Well, we just it's simple. We just talk to someone who came up with this, or someone who understands mathematics well, because it's a function. It looks like very mathy. So maybe we can talk to math professionals, so people who understand mathematics, and they'll tell you if there is a function and you want to minimize or maximize the function value. In this case, for example, maximize. You use something that's called derivative. You probably heard it from calculus, from your high school calculus. And the derivative actually shows you a direction, in most cases, in direction of maximizing the function value. Since here we have a weight, not just one weight, so it's not 2D in reality, because we can have thousands and millions of those weights. It goes to the land of multivariable calculus. Don't take it as something scary, because it just means the same thing but just for multiple variables, right? And when you go to multiple variable calculus, the derivative there is called the gradient, right? And the gradient is nothing more than a vector that shows you where to go to maximize or minimize the function value, right? So there's no neural networks here, there's no machine learning, this is just mathematics, right? So it tells you that this gradient thing just gives you a vector that shows you a direction. It shows, if you just take the gradient, it shows you the direction of how to maximize the value. If you take the negative gradient, which is a descent, right? So gradient descent, that's what it means. It shows you the direction of how to minimize the function value. So it's almost done in this exercise. There's one thing that's missing, right? So we know it's a vector, right? It doesn't have it's like a vector of a minimal size. There's a limit, a mathematical limit. So it's an infinitely small vector. It just shows you the direction. So, but how far do you go? Like if you go here, for example, your loss can end up a lot higher. If you take a smaller step, right, you can go for 1 million years before you get here. So how do we get there? And this step size, it's sometimes referred, and most of the time referred as a learning rate, is what we choose to figure out how to figure out which step to take. While this is mathematics, and mathematics tells you, this is gradient, this is for sure the direction to take to minimize the function. Learning rate or step size is a work of art, right? So there's no real, there's some guidance, but there's no real way to say, okay, for this particular problem, think about it. There's like millions of weights, right? How do you know what that learning rate is? So sometimes, given you work on it a lot, and you have certain problems and you know your data, so you choose You choose this learning rate, you see it doesn't work for you, you choose another learning rate, and so forth. But basically this is how you move down, right? You move here, learn again, move here, learn again, and finally, hopefully, you'll get to this global minimum. So if we ask this question again, how do we choose better weights? Well, we just take a step in the right direction, right? So that's exactly what it means. We take all those weights, all those random numbers that we just came up with randomly, and we say, hey, when I see your results, it's okay, but it could be better. So go back and adjust your weights, right? So go back and say, hey, weights, you're now weights minus learning rate times the direction times the vector. And if you want to impress, right, if you just want to come out of the stock and impress, you can just do this. Right? This is very impressive. It means the same thing. It's a little more convoluted for no good reason, but it's exactly the same thing. So W means all the weights, right? That's with capital. And A means learning rate, because learning rate starts with alpha, I guess. And then this thing means gradient, just a vector. So that's probably the only thing that makes sense here. And the J is a loss function, and W is weight. So loss function is also the weight. So it's exactly the same thing, right? And remember the back propagation that I told you about. That's exactly what it's doing. It goes back and says, hey, you friend, I know you have your own weights, so why don't you update your own weights, given the certain learning rate and taking the derivative. This whole thing is a function, so it happens in one pass. It's just math. And look at that. We just learned, in this case, a new weights, right? So we're already better. We're not there yet. We're going to go back and forth until we're at the point where we say, okay, this is good. This is not 42, but maybe it's 41.9, and it's good. But this is basically how we go back and update those weights and how we learn. And there are more jargon that I'm not going to go to. So there are more things that if you find you can kind of understand this or have an intuitive feel for this, you can definitely go and read about this. I guess this tree would probably complete 90% of the neural network knowledge that you need in order to go and build neural networks. But this is just too much to fit in the 45 minutes. Also very important, but not as important as intuitive understanding of layers and weights and how they fly back and forth. All right, back to Groot. So let's look at what we're going to use. Right. So this is something more flesh and colory, and whoever fell asleep, wake up. We're going to look at something that has to do with computers and pressing buttons. So we have this all tools that we can use in. Maybe there's more tools, right? There's a lot of tools, and of course, certain people prefer their own tools, and certain people do not like certain tools. For this particular example, I'm going to use two of these. I'm going to use FastAI, which is, by the way, an amazing deep learning course or machine learning course to begin with. It's probably the best. And the FastAI, it's a library. This is a brain API on top of PyTorch, which is an extremely simple and great Python neural networks library. And since I like Clojure is my language of choice, unless I'm doing machine learning, I'm going to use something that's called MXNet. And MXNet is the Apache project that's supported and used widely by Amazon. And it has Clojure bindings. The cool thing about MXNet, it has this. It's written in C++, but it has all the bindings for all the different languages. So you can train the model in one language, export it, and then keep training or keep using the model in a different language, which is pretty cool. And it has JNI bindings for Clojure. There's some exciting work in tool space, exciting to me. There's, of course, the tools are yet another huge topic in machine learning. And so what we're going to try to do is we're going to look at. We're going to see if Groot can detect humans. This has something that has to do with computer vision. Then we are going to try to write novels as Leo Tolstoy would. Something that has to do with natural language processing. Then we're going to look at natural language processing again, but this time we're going to take reviews written by people about wine, and we'll figure out, they're probably talking about Pinot Noir or something. Also NLP, but a different problem, classification, rather than producing text. And then we're going to look at collaborative filtering. You guys might heard of it as recommendations. It's basically I'm going to see what my friends liked and the movies in this case, and I'm going to figure out. I'm going to filter it collaboratively, and I'm going to figure out how I would rate or you would rate this particular movie, right? And in this case, I can sort them by those predictions and kind of recommend them to you. So without further ado, let's jump into code. Show. So I have my notes here. Right. So we are going to be running at the Google Cloud. So the reason we're going to be, is it big enough for you guys on the back, the font? Awesome, thanks. Yeah, so we're going to be looking at the reason that we're running on Google Cloud is because, this GPU things don't come cheap. And I didn't talk why we need to run it on GPU versus CPU, and I apologize. You can guys go read about it, but basically GPUs for this are faster because this particular guy has 2,600 cores, for example. They're little, but it's 2,600, right? So this particular graphic card is probably like $2,000. So I decided that it's probably easier to get 300 credits on Google Cloud than pay $2,000 for it. But this is why it's remote. This is why I hope that Wi-Fi will hold. And so I'm there right now. I'm on that box on the Google Cloud here, just in the REPL. So this is Clojure REPL. Well, I don't need that. So what we're going to do is we're going to take an existing model. Let me just show you the picture. So we're going to take the existing model that's called ResNet, and we're going to do something that's called transfer learning, which deserves yet another talk. But basically, the idea is that you have this neural network that we already looked at, right? Those circles and lines, and it's already trained. It already knows how to, recognize, chairs from a floor, ceiling from the eyeball, just because it's trained on something that's called ImageNet. In this case, it's like 14 million images, and they have 1,000 classes that that neural network is able to classify them. So that neural network already knows a lot about a lot, right? It doesn't know exactly about humans or how to detect humans per se, or my particular settings of my door viewer. So in order for this neural network to know that, I'll just remove a couple of last layers, and I'll add my pictures from Groot, right? And we're going to try to see if using that previous knowledge of corners, faces and all that, trees, it's able to figure out to fit my own problem. So I'm gonna here I'm just loading. Let me actually make it bigger. I'm loading the images. Okay, you can see that I have something that's called train and valid, and this is a very common approach. Sometimes you also have test. You have something, you have a data that you train with, right? So data that you pre-label, for example. Not necessarily there's a difference between supervised and unsupervised learning, but in this case, the training data is I took 1 day of each month from my camera, because the surroundings are different. There's snow, there's summer, there's more green, less green. So 1 day of each month, I thought it should be enough, right? And basically I classified them myself. I say, I see humans here, I don't see humans here, I see humans here, so forth. I classify them into 2 groups, and then I separated, say, 80% of that data will go into train, and rec is just a single file containing all the, and 20% will go to valid. I'm not going to use that valid. I'm not going to use the 20% to train my neural network. I'm just going to use it to validate whether my neural network is able to predict the humans successfully. So now we have this data loader, and we're going to create a model. Right, so this model is ResNet. We're going to use only, so ResNet comes in many different layers. So this is 18 layers, a small model. There's also 34, 52, all those layers, 152, and so forth. So I always like to experiment with the little data and little models, because if I see the approach is right, then I only go for, because it takes time, right? So in this case, we're going to use this kind of, and let's just try to, enough talking, let's try to train it. All right, so now what's happening, it just loaded those pictures, created this architecture, this neural network, and now it's going to put those pictures into this neural network by batches, right? So because the GPU still has, a limit, right? You can see that the GPU, well, you don't see GPU right now, but the GPU, for example, in this case has 8 megabytes, right? So I cannot take all the images and put it right away. So I take, batches of 10 in this case, and epoch, if you remember, is that one time we try to take the test, right? So epoch 0 means, if epoch 0 is done, that means we saw every question or every image. In this case, we just go and train this epoch 0, but you see it's kind of slow, right? 18 samples a second, not very good. So let's try if we can do better. So the reason it's slow is because by default, we train it on CPU, right? So I created a new model that, in this case, I say, hey, this box has a GPU. I know that. You should know that too, right? And then it has 1 core of this GPU, but it should be good enough. So let's see if we can do better with the GPU. So we fit the model, and we can actually see that GPU start cranking, right? So actually using the GPU, because before we were not, and uses some Bitcoin power. So you can see that the speed is way faster, right? And of course, having more GPUs or more cores is going to be enormously faster than CPUs, right? And this is in this case we trained on one epoch. The accuracy is 82%. That means that 82.9% of time the model was successfully predicting that this was a human or this was not a human. And this is, I mean, it's not a great model per se, but we also only use 18 layers here. Oh, well, sorry. Right, so we only use ResNet 18. So if we can do more epochs or use a different ResNet to make it better. But I already have this model kind of exported. So I'm going to go. I'm switching back to my laptop here, and I'm going to run the same. If I can, I should be able to. Yeah, I'm going to run the same thing here, but in this case, I'm going to use CPU, and I'm not going to train it. I'm just going to do something that's called inference. And inference, hence infer here. Inference is basically, given the image, and you already trained this model. The model is nothing more. This neural network is nothing more. The trained neural network is nothing more than a mathematical function. This has an input and has an output. So the part of inference, CPUs are doing really, really well because they're just running formula, right? So we can actually look at some pictures. 1 second, sorry. So let's look at this picture. Right, so I don't know if you can see it, but basically there are people coming into my house, right? And I would like Groot to say, hey, I detect humans. So let's see if Groot will be able to tell me that. Oh, there's no model. I forgot to create a model. 1 second. Actually, I need to load the model first. So I did export the model, but I didn't load it on my laptop. So let's just load it. Bam. Okay. So in this case, you can see that, remember that cross entropy thing, that binary classification that we did? There was 0 and 1, and how much if it's a 0 and how much it's a 1. So in this case, 0 is human, and non-zero or 1, it's not human. Right, so in this case, model said, okay, you gave me 2 classes to train with, right? And you remember by the picture, I removed the 1,000 classes that ResNet was trained with, and I replaced it with 2 classes that I need for my model, right? So now I have only 2 classes to predict. It of course makes it a lot simpler. So in this case, the model were able to tell me, and it's fast. It's CPU, and the inference is pretty fast. It was able to tell me that 91% of the time. Well, sorry, 90. I'm sure that there's a human in this picture. 91%. I'm sure 91% was the right way to say it. I'm 91% sure that there's a human in this picture. Yes. All right, I made it. Okay, so I mean, you probably get the gist, right? So we have more humans. Right, this is me. This is snow, a different environment. That's why I needed to take different images in different months. And of course, like here you can see it's. Did I use the same? Yeah, it's the same idea. And if there's no human, I'll just show you the last one. I think you get the gist. So there's no human here, and the model tells me. Yeah, and the model is 99% sure that there's no human here. So now I can hook it into my camera, right? When the Groot takes an image, I can run it through this inference since it's quick, right? And I can say, do you think there's human? Yes, then save the picture and back it up. If you think there's no human, don't save it. I don't need it. I don't care, right? So I still use the motion software, but I kind of make it. I can make it a little smarter, which is cool. So this was Groot, and let's go to Leo. And Leo here is Leo Tolstoy. Let's see if I can make it bigger and better. All right, so basically here, sorry, I forgot to mention, so this REPL thing and the black screens and all that, I was using Apache MXNet. You could probably infer it from the name here somewhere. Yeah, maybe here. Right, so now I'm going to switch gears a little bit, and I'm going to use the Python PyTorch framework, neural network library in this case. And there's fast AI APIs on top of that library. So, and that's in Python. right? So in Python, usually in Python, especially in machine learning or deep learning, you use this notion of Jupyter books. It's basically this, online notepad, if you will, where you can run things, right? You can run things inside. So, like I'm just showing you that I can run things, right? So basically, I don't know. The idea here is not to run things, and just for me showing that you can run things. Basically, the idea is that I took, I took some works of Tolstoy. You guys probably know this one, War and Peace, but it so happened that Tolstoy wrote more books, so I took some more. And the idea here is also, we're going back to this transfer learning thing. So there's this awesome model and awesome data set, which basically took, I think, like 30,000 largest Wikipedia articles, right? And it basically took a huge neural network and that didn't know much about English or much about language, and it basically tried to teach the neural network how to speak like Wikipedia article does, right? And by the end, I think this particular one trained for like 3 or 4 days, and at the end it was like 100 million tokens. Like a lot of tokens here means just weights, those weights and biases, and at the end, the model here was created that was able to predict the next word. For example, you give it, a certain sentence or 3 or 2 words, and you say, "Hey, predict the next word." And the model was, I think, about 30 or 33% accurate predicting the next word. It's like, think about it, it's crazy. Like, it's 30,000 articles, about everything, and the model is able to predict the next word 30-something%. And while Leo Tolstoy could care less about Wikipedia, he actually also, we're going to look at translated works of Leo Tolstoy, of course, translated to English. But translated works really care about whether the model already knows how to speak English, and that's basically what this model knows how to do, right? Maybe not good, maybe not well enough, but it does know something. So we take the model here. This is not really interesting, but basically we take take our Tolstoy work and put on top of that model, train it. We're just going to do this. We're just going to try to see if we train the model, right? In this case, it's the 33%. It was 33% accurate predicting the next word in the Tolstoy novels, right? Using that previous Wikipedia model, and we train it for 25 minutes. Not that bad. So let's welcome to the Daily Show with Leo Tolstoy. Let's see. So for example, I gave it, I gave it some words, different strokes for different folks, right? And the rest. So for some reason it decided that it's an end of a sentence. That's why it put a period here. The rest is basically everything that model created, right? It's word by word. So let's give it a go. So the skin is beautiful and fine. Its breadth has been replaced by the ring and its corners. The hood of the emperor's cap, tied to its so-called rather angry, proud expression, was set. So you can see that this is interesting, right? This is a model, actually a computer writing the text, mimicking the Tolstoy translations, right? We can try another one, like a French army soldier would never have approached Napoleon. This is something that I gave it. And then it knew that it's not an end of the sentence, so it added without any immediate intention. Makes sense, right? So and so forth. Like, you can see that some of the things are not very cool. Like, for example, the prince entered the French army from raised sides and dragged his head to a place where the general was moving by the way. Probably not Tolstoy. Maybe Tolstoy fell asleep and just wrote something afterwards. But it's definitely some gotchas here. But you can see that it's pretty powerful tool. I mean, you can only imagine this, and this is called the language model, right? So this model by itself is not very useful to kind of go and use it and generate some Tolstoy. But we're going to use this model later if there's time to build something more interesting on top of it. So this is Tolstoy show. Now we're going to look at, actually, let's do it now. So here we're going to use the same approach. This is also NLP. If you remember, there's this wine prediction thing that I talked about, this thing, right? And so here we're basically, there's this crazy guy who went online and he scraped all of the wine reviews he could find. Basically, people write wine reviews, and he just scraped them and classified them, right? Because on online it was obvious what was the wine the reviews were for, and he scraped, I think, 130 or 150,000 of those reviews. So we're going to try to build a model that's going to look at one of these reviews and say this is this wine, or this is to classify the wine, basically just based on people, all the sarcasm, all the jokes, all the slang. It doesn't matter, right? We're going to use the same approach. We're going to take this Wikipedia thing. doesn't matter. That's just my comparison with other white papers that I found, and it seems like this actually beats them. Sorry for scrolling. So we're going to take this Wikipedia model, right? The same thing we did with Tolstoy, and we're going to we're going to take these reviews, and we're going to take a couple layers off of the Wikipedia model and add the reviews on top, right? So first we're not going to be able to classify them, but first we're going to create our own language model that are able to somewhat understand the reviews, right? It's not going to be able to understand what those reviews are for in terms of what wine they're for, but at least it's going to be able to understand that this sarcasm probably means this or something like that. So we build that model first, and since it's an interesting thing when you build something more domain specific, right? Because wine reviews or healthcare or anything tend to be more domain specific than just English, right? So you get a higher accuracy. Because there's more of the same, right, in those reviews. So we have a almost 44% accuracy predicting the next word in the wine review, which is pretty cool. So then here's the kicker for this. So then we're going to create a classification model. We're going to say, okay, I already know the vocabulary that you use. I know the model. There's the encoder somewhere. It doesn't matter. So I know the model. I know the vocabulary. So let me try to classify wines now. And so I train. This took a little longer, hour and a half, but I got it to 76% accuracy. In this case, it's F-score is a little better, but it doesn't matter. So it's like say 75% accuracy. That means that I take a random wine review from the web, right? Or you can write it if you want to, and I'll put it through this model, and there's 75% chance I'll know which wine you're talking about. You don't have to name the wine. You don't have to name the wine in your review. It's just because different wines have those connoisseurs. They know all this little chocolate, marmalade, whatever those. I don't know those connoisseur words, but basically it's interesting because I don't have to be a domain expert in wines to build this model. That's interesting. So this is something that's called confusion matrix. It's a very quick and very useful way to know how your model is doing in terms of classification. So for example, I can see that I was predicting, let's say Riesling, 82% of the time. This was the actual Riesling, and this is I predicted or model predicted that it's Riesling. The rest was not as good. Like 11% of time, I predicted that it's Pinot Gris, for example. But it's kind of it's somewhat clean, so you can already use it. And then you run your predictions. But basically, this is the idea, right? This is another step. So you take a language model, you build another language model on top of this language model, right? To meet your domain, to focus your domain. And then from that, you can build classification models to say, okay, I know how to speak English. I know how to speak English and I understand wines now. Now run me through these classifications and let me figure out those weights, those millions of weights, and figure out what wine there is. So that's that. And then we're going to go and build recommendations. So this is a completely different thing, but it's also very interesting. So traditionally, even with NLP, natural language processing, neural networks were not very used very much for NLP. There was like word-to-vec, word embeddings. There was many other tools that were used in dealing with words and text. Like what's the frequency of this word here? What's the sentence? How it's constructed? Like neural network doesn't care how it's constructed. What's the nuances? It figures that out, right? Because it just math. It just goes gradient descent, better. Gradient descent, better, right? So this is another example. It's called collaborative filtering. And this is also neural networks were not used here before, but basically, you know that your friends liked or disliked certain things, and you can figure out, what that other person would rate it as, and not just yes or no. You can actually say 4.2, right? And we're going to do that. So I took a movie lens database, which is a very common database to predict movies. So these are the movie reviews. Yeah, that's a full screen, unfortunately. But basically, this shows you the most reviewed movies in that database. Right, you can see that you probably can recognize some. Forrest Gump, Shawshank Redemption, Star Wars somewhere here. So this is not when you work with data. Usually, you want to know when you put it on neural network. What I usually do, I spend a lot of time in the data itself. Right? I want to understand the data. I want to see what the data look like, how it's distributed. What I need to pay attention on. With the traditional approach is also the same, but in traditional approach you have to do a lot more feature engineering than with neural networks, because neural networks are very, very good at figuring things out. But it's good to know the data that you work with. So in this case, I'm helping out the network a little bit. I say that I know that reviews are from 0 to 5, so I'm giving you this range. When you predict stuff, try to put it in this range. This is actually a big one to be more accurate. I do certain things. It doesn't matter. So my final model is this is a different score. This is not exactly an accuracy, but I think you have to take a root of this. So it's like 90% accurate. So let's just look at it. So let's go to production because it's faster. And we can test in production. So basically, I took a random user, 210. Oh yeah, I forgot to tell you. So the way the data is organized, the way that I organize the data is I have user and ID, right? I have movie ID, which I don't care about. I have the rating, and I have the movie title, right? So basically, once I trained the model with this accuracy, I took a random user, the 210, I think, and I said, show me, since I know the rating for all the movies that user haven't seen. Well, I know the approximate ratings. I take the top movies that the user would like, but the user hasn't seen yet. And these are the movies, right? And you can see that these are some good movies, and you can probably see that this user probably likes, some actiony, or users are different. And I can do reverse. I can say, give me, so these are the movies that the user would like the most, and I can do reverse. I can say, give me the movies the user would like the least, for example, just for. So I don't know if you saw these movies, but these are not very good movies, right? So it kind of makes sense. Well, you would be surprised. For some users, actually found some crappy movies they actually like. There are actually some users that like specifically crappy movies for some reason, and that's interesting. I mean, you wouldn't know that, but that's the case. Okay, so Scratchpad. Okay, cool. So I just didn't want it to overload you guys with the rest, but this is basically the gist, right? I already know what awaits. It already evaded. Okay, so yeah. So now I'll just go to questions, right? Okay. What do I do? Thank you. Okay. All right. Do you guys have any questions? Not. I'm sorry? What? So the question is what challenges I faced during what? During implementing any kind of neural network? Well, I think the biggest challenge, for me, it's two bigger challenges. The first is data, right? Is to understand data well and to understand what you need to do with it. And the second would probably be, so neural networks are, while they're so great and so they generalize well, the problem with neural networks is they kind of this little fussy babies, right? You have to do just the right proportion of milk, the right proportion, that learning rate that I talked about, and so those are the two kind of angles. But in reality, this is more of a fun playing game rather than a challenge, if you will. But also it's important to follow the latest research because there's a lot of stuff that comes out. And while while this seems foreign and maybe too mathy, like as you read more and more about it, it becomes a lot more natural. Like I don't understand this huge formula maybe, but I understand the gist, right? And I can see if I can implement something similar to this. So it becomes, but this is definitely a challenge, like to understand because people in this industry, they like to be very clever for no good reason, right? So these things are in reality, a lot simpler than those scary formulas and white papers that you would. So it's bridging that gap would probably be the most challenging. Yeah. Oh, how do you choose the number of layers, epochs, etc.? So the most correct answer. So how do you choose something? Is you try something, right? So for example, you would definitely not try. Sometimes you could try not to have hidden layers at all, but usually when you build a network, you would build it maybe 5-6 layers. Input, output, and some layers in the middle, and those layers also have sizes, right? So the layers may have 5 circles, or may have 5,000 circles, right? So that's another dimension you have to play with. But again, that goes back to the neural networks being very kind of gentle. You have to be very gentle with them. But there are certain problems that are already figured out. So for example, if you do image recognition or some with images, you just use ResNet or some other models that are pre-trained for that. You just add your own layers, right? So there, for example, with this collaborative filtering, is nothing more than just they're just two layers. They just you can use neural network, but you can solve most of the problems with just using two layers. And for movies, for example, and for users, and just multiply those matrices until you get the good result. So epochs is a simpler one because as you train your model, you can see that the loss goes down. When the loss starts going up, or there's something called overfitting, but it doesn't really matter for this context. So when the loss stops going down and starts going up, you probably trained for too long, right? If it takes too long, maybe you should take a smaller batch size or smaller chunk of data and try it more epochs. So again, this is more of a experimental. Oh, more questions. When are you trying to find the global minimum? How do you know it's the global minimum versus a local minimum? Yeah, that's a good question. So the difference between local minimum and global minimum is, remember we had this graph here, right here, right? So we had this graph, and I kind of assumed that this is the only minimum that I can find, right? This is not really true in practice, because in practice, think about this as the practice, this things is never that smooth. It's very wavy, right? And sometimes I can get into a thing and I can think it's a minimum, but it's not a global minimum, it's a local minimum. So you don't know whether you get to the local minimum, but there are tools to prevent that. So there are tools to say, okay, you are in the minimum now, so your learning step was very little. So now try this thing called momentum. Now try a larger learning step. Try to get out of it, and try it here. Now try to get out. So there are certain tools and ways to kind of get out of local minimum. Sometimes you can't get out of local minimum, or it's very hard to get out of local minimum and you get stuck there. So it happens. Okay. Is that mine, I guess? Demo code available on GitHub. Well, some of it is, some of it I will probably make available. I just don't want people to look at my house pictures. But but this is there's this thing called MX term. You can go and read about it. Don't mind that it's closure. It doesn't matter. The cool thing here, it kind of explains you a little bit about transfer learning and the models and why I did certain things I did. Right? You kind of give you more context. You can always contact me. I'll share the reasoning behind it. But this is probably the first thing I would go to here. And as far as these notebooks, I will have them available like for some. I'll depersonalize them and make them available. Okay, more questions. Any library stack recommendations on how to do sentiment analysis with neural networks? So what's a sentiment analysis? Sentiment analysis is when you, for example, remember we had wine reviews. Imagine we have movie reviews now. And the sentiment analysis means that I look at the review and I say this is a positive review, right? Or this is a negative review. So I analyze the sentiment. And the sentiment analysis is the same tools, all these tools that I showed you before would be able to help you with that. But I use PyTorch because I liked it the best. I'm not saying it's the best, I just like it better, or FastAI in fact. And that thing allows, remember you build that language model, and after you build the language model, you can classify positive, negative quite easily because it's just two classes, right? So those tools, all these tools in fact will work. Time's up. Okay, I'll choose one more question. Whoa, that's a lot. Okay. All right. Last question. What other ML techniques were considered along with genetic algorithms, K-means? How did you start? Yeah, so this is the question about traditional machine learning versus neural networks, right? And traditional machine learning has a lot of tools because it's been a lot of years, and such as K-means, genetic algorithms, word-to-vec, and all that. The boosting trees, the random forest, and those tools are really, I think they're really cool for narrow tasks. Like for example, I often use something that's called random forest. Random forest is just a decision tree to actually see if I can find a better parameters for my neural network model, right? So I do use them. I don't specialize in them. I know quite enough about them, but I don't really use them day to day. So neural network is just such a good tool for generalizing and generalize such well enough. So I use neural networks and random forest. For random forest is from the traditional machine learning, and I have a look. I know that look. All right, thank you. Thank you, guys.